Good afternoon, everyone. I just want to say welcome to the Project Staple pitch event. Thank you all for being here. Just so you know and so you're aware, this event is being recorded so that we can post it at a later date and share this with everybody. To start off, my name is Angela Austin. I am a program manager at Ensign, National Security Innovation Network. If you're not familiar, Ensign is a program office in the United States Department of Defense. We're nested within the Defense Innovation Unit, and we're a problem-solving network. So our mission is to build networks of innovators that generate new solutions to national security problems. And so here we have a problem that was brought to us by the Army Space and Missile Defense Command. I'm going to introduce you to Alex Stoicki-Goldberg, who is going to talk more about the problem set that we have here and why this is important. He is a Joint Technology Acquisition Innovation Officer with Defense Innovation Unit. Stoicki, please go ahead and share with us more information on this organization.
Appreciate it, Angela. Thanks for all those that have participated in this particular program that is led by SMDC, the Space Missile Defense Command. We also have on the line folks from the Defense Innovation Unit. There's a number of reasons why we want to be able to leverage these capabilities of looking at specifically the platform of new novel ways to be able to do both kinetic and non-kinetic capabilities. Everyone's proposals were, ranged from capability, and we were really excited to see the varying approaches to getting after it, and really look forward to dialing a little bit more about individual companies' capabilities, maturity levels, and how we can get after it. So appreciate for everyone being able to participate and look forward to hearing everyone's pitch.
Great, thank you, Stoicki. And before we kick off our first pitch, I'd like to just give a quick overview. So we're going to have 8 different companies here today pitching their technology. We have a pre-recorded pitch that's going to start. It's going to be 5 minutes of pitching, followed directly by 5 minutes of Q&A from the judging panel. And then following that, we will have 2 minutes of hold period for the judges to get in their final scores, and then we'll go into the next company. And so to start off, we are going to hear from Andrew Army with Commit Technologies. Megan, we can't hear anything.
From Andrew Armour, not hearing any of our comms or sounds going on with this.
Saying no audio.
Okay, 1 second. Let me try this again. Let me know if you can hear this now.
Hi, my name is Andrew Armour, president of Commit Technologies, and presenting.
That sounds pretty good.
I've got with me Dr. Robert Zubrin, who has extensive experience in working with balloon technology. We're going to start out with a couple of videos showing where we've been and some of the COTS Pegasus balloon solutions that we're going to be employing on this project. This is the Pegasus solar balloon being hauled out to the launch site in black and white. You have a hydrogen-filled balloon that's providing lofting at altitude, about 2,000 feet. The solar balloon is going to be cut away from that. At that time, it's going to inflate and go up to about 50,000 feet and stay there until sunset. These are the flight camera views. You can see that with just a cheap setup, and in this case, a GoPro camera, so nothing special, you're getting ISR views that can be extremely relevant to a battlefield commander. And you can see the flight profile there as well. I believe this flight is about 540 miles and could go even farther.
I'm not sure you guys are seeing the video moving, but I'm getting comm, but no video on my end.
Released at 12,000 feet from a
Yeah, the video's frozen for Clay as well.
instantaneous inflation, as you can see from this video.
I'm sorry, what was that?
Yeah, we've got comm right now, but the video is just frozen on a particular screen, at least from commit. That's what we're seeing.
Yeah, same here.
Let me rewind it a bit. I apologize. Let me know if we run into the same issue.
I believe this flight was about 540 miles and could
Yeah.
run.
So I'm not seeing any movement of the video, unfortunately.
Not seeing the video. Let me stop sharing and reshare my screen. Is this better?
That looks right.
Okay.
We might want to go, if we can, go back to the beginning, just because I think we missed a fair amount of content, but
Okay, Angela, should we just start and then hopefully we don't have this issue again? I do apologize, folks.
Thank you, Megan.
All right, let's try this one more time.
Hi, my name is Andrew Arnold, president of Commit Technologies, and presenting the higher concept. I've got with me Dr. Robert Zubrin, who has extensive experience in working with balloon technology. We're going to start out with a couple of videos showing where we've been and some of the COTS Pegasus balloon solutions that we're going to be employing on this project. This is the Pegasus solar balloon being hauled out to the launch site in black and white. You have a hydrogen-filled balloon that's providing lofting at altitude, about 2,000 feet. The solar balloon is going to be cut away from that. At that time, it's going to inflate and go up to about 50,000 feet and stay there until sunset. These are the flight camera views. You can see that with just a cheap setup, and in this case, a GoPro camera, so nothing special, you're getting ISR views that could be extremely relevant to a battlefield commander. And you can see the flight profile there as well. I believe this flight was about 540 miles and could have gone even farther. These solar balloons have been demonstrated being flown out of aircraft, with this particular released at 12,000 feet from a Cessna 182 with near instantaneous inflation, as you can see from this video. In 2022, Commit Technologies, in conjunction with Dr. Zubrin, launched on back-to-back days a glider attached to a high-altitude balloon and released them from approximately 60,000 feet, as you can see here. In both these cases, the glider autonomously navigated after release from the balloon to a pre-coordinated location. In the first case, Hudson, and in the second case, Kyle. Using the technology we just demonstrated, we're going to create deployable solar balloon platforms to achieve a wide variety of missions with very tailored capabilities. These solar balloons are being launched ideally off of a quadcopter or other launch platform as applicable. With a quadcopter, we can take 2 minutes to deploy and launch that first balloon, and then to recover and reload maybe takes an additional 4 minutes for a 6-minute cycle time for a single minimally trained operator, and this can be increased by adding the number of quadcopters there. 15-mile-per-hour crosswind is definitely achievable, depending on the launch platform. Even significantly higher is also achievable. Just as in the video, we're looking at autonomous operation post-launch of the balloon, 22 pounds for initial solar balloon capability to lift. And then if we add hydrogen to that balloon system, then it can lift up to about 100 pounds and exceed 24 hours in operation. Our novel open architecture provides modular navigation capability. We're able to put a vent valve on the solar balloon to control the altitude and thereby control where it is navigating to a much higher level of precision. If we want extremely precise navigation, then we attach a drone, as you saw in the video, put the payload on the drone, and then release that up at altitude, allowing the drone to then navigate itself to a location and then stay overhead. Easily, that drone will be able to stay on station greater than an hour, provided we put some electrical capability on that. And then we can continue to adjust to meet customer needs and DoD interests. Provide the required power. We're using COTS batteries. This is a low cost, low weight, simple solution to provide the power that you need. For the architecture, we're using RD Pilot, so it is open software. The government, as well as us, as well as another vendor, would be able to easily change the parameters, as well as completely simulate the mission that you're going to go execute with the drones over target. For the balloons and cutter boxes, these can be produced at less than $1,500 in LRIP, with that price able to be lowered as we get to mass production, and capabilities of 1,000 per month are absolutely possible. We can source gliders from a variety of sources depending on which type of mission the DoD wants us to do. For the proposed demonstration, we're open to changes from NSIN, but we would utilize either Commit Technologies heavy lift quadcopter or a surrogate balloon to loft the solar balloon up to its inflation altitude. It would loft a 12-pound weight on the solar balloon at 50,000 feet. It would also release a drone that we have attached to it that will navigate to a specific location to show that capability while we continue to monitor the solar balloon throughout the day to show its endurance. There are multiple stakeholders in the commercial market, including Ford, MODs, special operations, and multiple other government customers. For myself, I have extensive experience both on the warfighter side and as an engineer and president of Commit Technologies. Dr. Zubrin brings extensive experience as an inventor, founder, engineer, and ultimately a visionary in the aerospace field.
Great, and with that, we'll go ahead and turn it over to our panel of judges to begin asking their questions.
Hi, Andrew and Dr. Zubrin. This is Gavin LaFlower. So I have just a couple questions on the concept of employment with the cutter box. Am I understanding that correct, in that the cutter box is attached to the latex balloon and continues going up until termination? And then if so, what happens to that cutter box? Does that just fall to the ground?
Okay, let me answer this. The latex balloon with the cutter box was used in that flight experiment because we didn't have a quadcopter handy. In an operational context, we would just use a lifting quadcopter and just drop the solar balloon. It then inflates like a parachute and flies up to 50,000 feet. Now, if it is carrying a payload like a glider, it would have a cutter box below it. And our cutter boxes are programmable. They can release the glider drone based on altitude, GPS location, time, or any other criteria that you might think of. So you could, for instance, launch the balloon easily from the ground using a small quadcopter. Quadcopter just flies up a couple of thousand feet and drops it. The balloon then flies by itself up to 50,000 feet. It can then fly hundreds of kilometers and at a pre-programmed location, let the drone go to do its mission, thus greatly extending the range of the drones, allowing them to be launched from outside of adversarial airspace, and many other advantages.
Okay, understood. So the cutter box is not consumed in use. The nominal configuration would be with a quadcopter that deploys it at approximately 2,000 feet.
Correct.
Yep.
And by the way, that allows us to do balloon launches without needing to transport hydrogen to the front, which is an enormous advantage. You should know these balloons are being used in Ukraine right now.
Do you make all of your balloon systems in-house, or do you purchase your latex balloons for the initial lift capability?
So Pegasus is going to be providing the balloons from a COTS perspective, and they are making all of them in-house. So that is a company that's owned by Robert Zubrin in Poland, and then Commit Technologies would be doing all the add-ins for basically all the government capabilities that we're looking at applying to this.
So in your demonstration, you had one thermal balloon to one latex balloon. Can you envision multiples and thermal balloons to the latex balloons? And what would be the limiting principle?
I think we could certainly do that, but I think that as Dr. Zubrin highlighted, we would anticipate probably launching it via a quadcopter, potentially a helicopter if you wanted to launch a bunch at once, but probably not really in an operational context using that latex balloon.
Okay,
Right.
Thank you.
And you should know the special forces here in Colorado Springs have launched one of our solar balloons from a helicopter, a manned helicopter. Test.
Going back to the manufacturing of the envelope for the solar balloon itself, how many can they produce per day? And are those hand seamed together, or is there infrastructure in place when it comes to ramping up for scalability?
Well, we could ramp up, but we actually have 2 factories in Ukraine right now manned by volunteers, and they've turned out already over 50 of the balloons. And the way we do it is they use a clothes iron to seal the polyethylene. We do not need specialized equipment. And so we have the women from the neighborhood of a local school sealing up the balloons with their clothes irons and then delivering them to the front.
Are there any quality control testing associated with your envelopes to assess their availability?
We inspect them, but you should understand that a small leak in a solar balloon has no consequences. In fact, if one of our balloons was flying and you were to put 6 shots through it with a rifle, it would not affect it at all. Because it's not like the rubber balloon would pop, of course, if you hit it with anything. But one of these, you just make a small hole in it. And since it's capable of reheating the gas, once it, in other words, you have some hot air, gas leaks out the side, new gas will replace it. And so long, I mean, yes, you could ultimately tear it to pieces with a lot of ordnance, but they're very robust.
Great, thank you. We're at time for the Q&A portion, so we're going to go into our 2 minutes of deliberations for the judges to get their scores in, and then we'll go into the next pitching company. Thank you so much to you both for Commit Technologies, your proposal. We'll go ahead and go into that break.
Thank you.
My name's Alex, and I'm thrilled to present Worldwide Aeroscorp's groundbreaking Dwell modular balloon system. The critical problems associated with high-altitude balloons are inflation, launch, and acquisition cost. The large size of high-altitude balloons makes the inflation process very difficult because it requires a large number of ground crew, specialized equipment, and poses significant safety risks with a high probability of balloon damage. As the world's leading lighter-than-aircraft manufacturing company, Aeros has developed, designed, and built 16 commercial operational airships, 2 certified airship models, and over 100 tethered aerostat systems, securing multiple type and production certificates for operational airships along the way. Our offerings include high-altitude LTA platforms, FAA type certified Aeros Skydragon airships, advanced tethered aerostat systems, and the innovative electrical variable buoyancy airship, the EVBA Aeroscraft. This unmatched record in the U.S. airship industry means Aeros has a unique expertise for developing lighter-than-air systems. Developing the Dwell high-altitude platform balloon system, we set to overcome a number of key issues with balloon inflation, overly complex launch procedures, and expensive costs of production. Our solution was to go modular. To solve this challenge, Aeros developed a 2-module system consisting of a lift module and an expansion module. The system can accommodate various payload weights and operational altitudes and even maintain mission altitude through flight duration with an altitude control unit. The lift module provides static lift to elevate the system to 300 feet, while the expansion module allows us to reach higher operational altitudes. The number of expansion modules attached to the unit will depend on the specific mission's altitude and the required time on location. With this versatile modular system, we can reach altitudes between 20,000 and 100,000 feet, accommodating payloads up to 50 pounds. In addition, only the lift module needs to be inflated on the ground. The expansion modules are folded and can expand at higher altitudes, allowing simple and rapid launch by just one person. Our modular balloon system is crafted from HDPE, which allows for simplistic design, low cost, ease of manufacturing, and remarkable durability. We've conducted multiple tests for strength, permeability, and production methods, and this works as advertised. With this material, a lift module and 2 expansion modules can reach 40,000 feet with a 12-pound payload, and the lift module and 32 expansion modules can reach 100,000 feet with a maximum 50-pound payload, all at an attractive price point. Our efficient production line involves 2 people per module, enabling us to produce 12,000 balloons per month. We anticipate reaching full-scale production and beginning deliveries within 3 months of contract award. We successfully conducted testing to validate the system's performance and range of communications. The Aero's electrical system allows for BLAS telemetry data, low cost and accurate APRS signal, and strong and durable quick release system for recovery. The large size of high altitude balloons means that for many systems, launch requires a large ground crew. Moreover, successful launch can often only be achieved in calm wind conditions. Both these factors significantly limit operational capability as well as availability. Our modular design requires only one module to be inflated on the ground, which dramatically simplifies launch procedures. As a result, one person can inflate and launch a balloon in less than 5 minutes for a payload of 12 pounds and under 10 minutes for a payload of 50 pounds. In conclusion, the Aero's high-altitude dual modular balloon system is a game changer in high-altitude ballooning, offering simplified one-person launch to reach unmatched altitudes cost-effectively and with rapid production. Thank you for your time, and now we're open to questions.
Appreciate it. Thanks, guys. Thanks, Igor. Let me open up to Gavin and Ben first with your questions first.
Do you guys have a prototype? Have you launched one of these?
Yes, we do. And done
Have you flown it?
One more time, sorry.
Have you flown it?
Yes. In single model and multiple configuration.
And what was your longest flight time for those flights?
Probably about 6 hours.
Thank you.
So I just want to understand how the expansion model functions. Are they connected, all of these modules together through a tube, and where the air expands from one to the lower modules, or how does that function?
Correct, you're absolutely right. It's expanding, they all connected with tube, and they expanding from upper to lower.
Okay. How do you bring the system down? What are the abort capabilities and the C3 for the system itself?
On the lift balloon, on the top balloon, basically it's simple cutter on the upper, on the lift module.
Is there a GPS, like a geofence that's set, or is this commanded through SATCOM? How do you communicate?
You can have 2 options, right? You can do the command through the SATCOM. You can apply through the boundary of GPS or altitude position. It's basically any option available.
And Igor, have you put those on the balloon? Have you tried those out where you actually do have a GPS or a SATCOM communication, or those things that you could put on in the future?
Yes, no, it's already done. Again, it's on one of the slides was showing on prototype level, but on the prototype level it was done.
Awesome. And you could produce 12,000 a month. What was that price point around for around that 12,000?
Yeah, as much as I remember, it's about 800. Trump can correct me if I'm wrong. I mean, the basic principle when we're able to achieve so low price and high production, we're using just tubular PTE film. What is making the whole heat sealing automatic and pretty simple.
Clay, do you have any other questions?
No, I think all mine have been answered. Thank you.
Gavin?
As far as launch considerations, what's the environment ground wind speed that you anticipate being the maximum to employ the system?
Practically, you probably can go to 20, 25 as personnel will train. I mean, theoretically, it's not limited because you inflating only lift model, what is pretty small. And everything else, it's packet. You don't deal with any drag or any forces of the wind. Right? You can hold the lift model in one hand.
Okay,
and if you have more than one, balloon, and like Gavin was talking about, if you have to terminate the balloon from the SATCOM link that you already have, does that go to the top balloon, and the top balloon then also cuts the bottom?
Top balloon.
And the top balloon will then drag down the bottom balloon?
Correct.
Okay. Awesome. Anything else, Gavin? Ben?
I'm good here.
No, awesome, Igor. Very, very interesting capability, very unique, right? Very interesting price point, and the quantity, and the fact that you guys actually have it flying. Appreciate the insight. Thanks for the help.
Thank you so much.
Angel, back to you. Great, thank you. We'll go ahead and start the 2 minutes of deliberations, and following that, we'll introduce the next company. Thank you so much.
Thank you.
And so we're ready to go.
We're going to hear from Jim Wickman with Aerostar International, and his pitch presentation will start now.
Hi, I'm Russ Vanderwerf, and I'm the Vice President for Stratospheric Solutions here at Aerostar International. Today, I'm going to be presenting to you our pitch for Project STAPEL, the National Security Innovation Network's long endurance, high altitude, small tactical system challenge. After the presentation, we'll be happy to take your questions. Let's get started. Aerostar International is the world leader in stratospheric lighter-than-air technology. We've been building high-altitude balloons since our founding in 1956. Over those 6 decades, we've consistently provided high-quality products to the U.S. government and Department of Defense. Our current product line benefits from those decades of experience, carrying payloads from less than 5 pounds to over 8,000 pounds safely to the stratosphere. Aerostar has operated over 2 million flight hours in the stratosphere with over 10,000 operational flights. Our flagship balloon systems today include Thunderhead, Cyclone, and Lightning, which we'll mostly be talking about today. In addition to these standard offerings, we can provide customized systems for payloads that have non-standard needs. We operate 2 production facilities, one in Sioux Falls, South Dakota, and one in Sulphur Springs, Texas, with a combined 8 production lines and over 80,000 square feet of capacity. Lightning is a rapidly deployable zero-pressure balloon system capable of achieving flight at altitudes from 50 to 80,000 feet with a wide variety of user payloads. It's tactical and supports mission durations of up to 2 days. It can be launched about anywhere, including off a Navy ship as seen in this video. The Lightning model includes ballast and valve for limited altitude-based steering, lithium-ion battery stack capable of delivering 1,000 watt-hours for payload operation, and command and control via satellite, Iridium SATCOM modem, or an optional S-band or C-band Silvus line-of-sight radio. In addition, Lightning is fully integrated into our Thunderhead command and control software. The Lightning system's standard payload interface provides power at 28 volts DC, up to 300 watts instantaneously, and up to 1,000 watt-hours of energy throughout the flight. We provide a data Ethernet interface, which feeds both communications for either satellite beyond line of sight or direct line of sight radios, and also provides GPS and INS information in real time to the payload during flight. And we provide a standard physical attach point layout, which is documented in ICD drawing, as well as a lightweight, easily available flight-proven gondola for those who don't want to build their own enclosures. We've already demonstrated the flight of a number of different government-furnished payloads, including visible and infrared comms repeaters of various waveforms and technologies, signal collection boxes, drop sensors, and electronic decoys. As we've discussed, the Lightning system is tactical and is designed to be launched by a crew of 2 anywhere in the world on short notice. In this video, you'll see 2 of our Aerostar team members who drove from our headquarters in South Dakota to the Badlands of North Dakota with only the equipment, supplies, and material that you can see in this picture and is fit in the back of a small pickup truck. That includes the launch gear, the balloon system itself, and the lift gas. The system can be launched anywhere in the world with less than 15 knots of wind and with no precipitation, and is a rapid and simple setup which can be easily packed up and moved on once the launch operations are finished. Our Thunderstorm software suite provides a host of mission planning tools supporting end-to-end execution in the stratosphere. We offer wind modeling and mission feasibility studies through our planning system, pre-flight checks for hardware checkouts before flight, and full remote piloting capabilities over satellite or line of sight through any web browser-enabled PC. All of our stratospheric platforms, including Thunderhead, Cyclone, and Lightning, are supported by this same software package, and we offer pilot training which can be used to train your team up to fly these balloons themselves. Aerostar's Lightning system meets or exceeds the technical requirements outlined in the Project STAPEL request. In addition, it meets many of the desired features requested already out of the box. While Aerostar's current price of the Lightning system exceeds the requested specification, we believe that with sufficient production volume and mission tailoring, pricing can close to the target goal. It should be noted that Lightning balloon systems are available today for immediate procurement and can be rapidly produced at scale in our facilities. In conclusion, we here at Aerostar really believe we're the right people to work with on this project. We have over 6 decades of building and flying stratospheric balloons under our belt. We're already delivering high TRL solutions for stratospheric flight to the Department of Defense, and our Lightning balloon system was specifically designed with these persistent, small team tactical operations in mind. Our payload flexibility and our integration experience means we'll help you get the job done no matter what the mission profile is. We're excited to answer questions now and hopefully to come demonstrate this system for you in the field. Thank you.
Appreciate it, guys. From the Aerostar perspective, one of the things in the slide was, right, the price point, right, possible. What was that? What were the variables that would make that possible to get to represent a price point? So it was kind of missing from the original pitch. if you could just talk to a little bit about that, of how do we get to the price point where we're looking for the small, cheap, attritable, right kind of balloons. If you could talk to a little bit about that.
Sure. And this is Jim Wickman speaking. So first off is the Lightning in its current form is a fairly low rate of production. So if we were to increase the production values, we think we could have a pretty good impact on the overall price. In addition, there may be some of the capabilities in the flight control unit that go beyond your requirements, in which case we could modify that electronics package to a smaller, less expensive form factor if your requirements don't require the current capabilities, and we think we could see additional savings through that as well.
Awesome, Jim. What scale would then get to that price point? I know you guys are in low production, but is it 100 a month, 1,000 a month, 10,000 a month?
Yeah, I think if we could get in the neighborhood of 100 or hundreds per month, we could see some pretty good cost savings there. We haven't calculated that, but I'm confident that we can get the price down below what you're seeing today.
Okay, thanks, Jim. Gavin or Ben?
Is this a zero pressure balloon?
That's correct. This is a zero pressure balloon, so it has a helium vent or a lift gas vent and a hopper for ballast.
And what's your current level of station keeping?
Let's see. So with a zero pressure balloon, the accuracy of your station keeping or station seeking is going to be somewhat less as you're constantly either losing lift gas or dumping ballast. So you'll see some reduction in maneuverability as compared to a super pressure balloon, but we do have the ability to tune the Lightning to try to take advantage of different wind layers at the stratosphere. So we can both increase and decrease the altitude to try to find suitable altitudes for refined navigation.
So several days?
We're advertising about 48 hours of flight time for the Lightning, usually not to exceed. It's the nighttime is what's the hardest on a zero pressure balloon. So again, depending on the completeness or how much navigation is required, I wouldn't look at it for much more than 48 hours.
Yeah, Jim, if station keeping wasn't of the concern, what is the driving factor for the 2-day maximum mounts? If it is the ballast and we're not changing altitudes, we're not station keeping, we have predictive winds, and we're just going to go with that. But what else is the driving factor for that 48 hours?
Yeah, I would defer to if Mark or Russ is on the line can address that question. We're getting into balloon now.
It's really just how much ballast is consumed, like Jim said. So when we get through about 2 overnights, it's a question of how much fraction of ballast you have versus how much fraction of payload. So it's also dependent on how much other stuff you have on there in terms of batteries and sensors and things. But that's really what's driving it.
Okay, yeah, I didn't know if it was batteries or whatnot. Gavin or Clay, let me open it up to you.
Yeah, can you guys go into the equipment required for the launch procedures again? I saw that your pictures and the video you showed, there was a vehicle required, a large clear area. Can you expand upon that more?
Yeah, in essence, the Lightning can be launched by hand with 2 individuals. Typically, if there's a higher wind or there's a larger payload, we like to anchor the crown. It just provides for a more stable platform when you're inflating the balloon and launching it. So while we do have a kind of a low footprint launch frame for it, it's not required for launch.
Hey, this is Gavin. I just have one quick question on an employment and training. You mentioned training up soldiers to employ it. Is this still contractor operated, or is this entirely government operated?
Currently, we operate it as a contractor project. We can and have provided training to government soldiers or other parties, and we have an established training course and protocol to turn that over to others. But currently, it's
yeah, Jim. Just another way to ask that question is, any of us can launch this thing, or do you need, you know, specialized training and right? It's actually very technical to actually launch this thing.
No, I would say, I mean, you have to go through the training class, but beyond that, there's no specialized training or education required to launch this. It's really just stepping through the class and having a couple of practice launches under supervision.
Great, thank you so much, Jim. That puts us at time for our Q&A portion. I want to say thank you, Jim, to your company for presenting this, and we're going to roll into a 2-minute deliberations period.
Yeah, appreciate it, Jim. Thanks, guys. Angela, we're ready to rock and roll.
Great, thanks. Next, we're going to hear from CalSCott Engineering, Suman Sarapalli, and we'll go ahead and get that pitch started.
Thank you for the opportunity to present our idea to STAPEL. I'm Suman Sarapalli, the Vice President at CalSCott Engineering. We're based in Lawrence, Kansas. We're an aero and defense engineering firm specializing in autonomous vehicles. My business partner, Tom Sherwood, and I set up this company in 2002. Since then, we have worked on projects for the Air Force, Army, Navy, DARPA, NASA, Department of Energy, NOAA, NSF, and a couple of three-letter agencies. Right now, we are prime contractors on 4 multi-year NASA and Air Force projects related to autonomous vehicles. For STAPEL, we are proposing a balloon-lofted high-altitude UAV based on work we did for a NASA Phase 2 SBR project. The electric motor gliding UAV is carried to altitude under a latex balloon or multiple balloons. The balloon reaches the desired altitude and then the UAV cuts away and loiters with an electric motor. Our overall loiter time at altitude will be in the 6 to 8 hour time frame. The key thing to note here is that we can collaborate with other teams who may bring balloons to the table. We can fly a UAV under their balloons. The critical piece we bring to STAPEL is funding. We want to participate in STAPEL in December to meet the SMDC and NSN customers, understand the requirements, come up with a design that meets STAPEL missions, and then get the effort funded under the NASA CCRPP program. We are also discussing vehicle designs with 2 other DoD end users to meet guidelines of the Replicator initiative. Our design for STAPEL aligns well with the Replicator program. Here is the balloon-lofted UAV we flew for NASA in Finland in 2015. There's about 10 to 12 pounds total weight, including a 4-pound air sample payload. We flew several missions with multiple UAVs, reaching as high as 80,000 feet. We demoed the balloon lofting, the cutaway, the gliding vehicle, the comms, and all the hardware that performed well at high altitudes. Cost. For an attractable UAV, we can bring some key lessons learned over 3 decades of building low-cost UAVs. We can repurpose items from non-defense domains, ripstop nylon, carbon and fiberglass poles from fishing and sailing, coupled with CNC machining, 3D printing, laser cutting. We've done all this for various projects. Our UAV will be an electric motor gliding UAV, which is optimized for cruise at near 60,000 feet. Right now, we predict a 30-pound vehicle with about a 16-foot span to be able to provide the endurance we need with a 12-pound payload. Cruise power is about 500 watts. We have 80 watt-hours available for the SMDC payload. We have traditional airplane configuration with high aspect ratio wing and a boom fuselage. Of course, we can scale up and down from there. The important thing to note here is that we are designing the UAV for the cruise condition. This allows us to drastically reduce the energy and power requirements for the vehicle. Also, since the vehicle is lofted to altitude under the balloon and is attritable, we don't have to design for takeoff and landing loads, and this reduces the overall weight of the vehicle. Okay, here is where I tell you that we are not well aligned with the schedule requirement for STAPEL. We will not be able to do a flight demo with our UAV in December for you, but we can indeed bring our UAV and our advisors to the demo and discuss the final details of our proposal with NCN and SMDC. Then in Feb 24, we can submit a CCRPP proposal to NASA with perhaps a letter of support from SMDC and NCN. In June 24 through September 25, we can build and demo version 1, which meets the threshold STAPEL specs. In 2025 to 2026, we can build and demo version 2 to meet the desired STAPEL requirements. In addition to the team members at CAPSCOT, we're bringing EOSS to the table, which is a top-notch team with hundreds of balloon launches done to date, including one done this weekend. For the CCRPP, we have our investor, Elite Global Equity Fund, with us. Here are some raw estimates for cost based on our experience in previous projects. I think the desired cost level for the low-rate production version is achievable, but I think the desired cost level for the high-rate production is a bit of a stretch. This slide shows what we bring to STAPEL in terms of facilities and equipment, hardware, software, flight vehicles, and test area. In conclusion, we'd love to participate in STAPEL, but we do have some schedule-related challenges for the December STAPEL mission per se. If we are able to form a strategic relationship with customers at SMDC now, we can bring $5 million from the NASA CCRPP program to build a vehicle to suit your specific STAPEL mission. It would be an honor to add this effort to the long list of projects we've worked on for national security. Thank you for this opportunity.
Appreciate it. Who's here to represent the company?
Suman Saripalli is here, along with Russ Chadwick and Don Nasanka.
Fantastic. So a lot of this was in regards to the payload versus the platform. So I had a bunch of questions on specifically the platform, because the focus is really on the small, cheap, attritable balloon. There are quite a few payloads that we have already that we would like to leverage said platform for. So what's the price point just for the balloons, the scalability of how many you can actually produce of these balloons? Maybe I missed that. If you can just highlight those.
Yes, so we are a little unusual in that what we are pitching over here is really the UAV, an attritable UAV that can be lofted under a balloon. It can be balloons that we've used in the past, like Totex, or they can be balloons that some of the other presenters here have put forward.
Yeah, and have you tested this up at altitude? What is the novelty of I'll pull the thread, even though this is outside the scope of necessarily the challenge per se, but in regards to, have you done, weather testing? Can it survive such cold weather up at, high altitudes of, being lofted at 70, 80,000 feet?
Yeah, we've had several flights of 3 prototypes that we built back in 2014 and 2015 under a NASA Phase 2 SBIR. And yes, we had multiple flights with them, and the cold temperatures, etc., are not an issue. We've selected to fly at where the the wind speeds are lower. So about at 60,000 feet, that's really a sweet spot.
And have you produced for, like, how many can you scale of these drones per se?
Pardon?
The scalability of the drones, being able to produce, right?
Yeah, so if you look at the cost slide, we can spool up the production. We think we'll be able to achieve the low rate production numbers. I think the price was under $11,000, but the high rate production, just things being what they are, even in high rate production, I don't think will be less than about $4,500.
Okay, and my last question: have you looked at a comm denied, GPS denied environment when you are flying these drones, as far as the use case?
Once you give them a flight path and an area. Now, if you don't have GPS, that could be a problem. Yes.
Okay, I'll open up to Gavin and Ben.
Yeah, so I have a question on just the payload capacity within inside of the glide vehicle. What can you put inside of that system as far as swap?
That we would right now, the device that we had on there, this is a much smaller vehicle. What we have shown over here, this is what we did for NASA for a very specific payload that we built for them, and that was a cylinder that was about 15 inches long by about 7 inches in diameter. But like I said, what we are here for is to get requirements for some future vehicle, and we can design the vehicle really to meet any particular size, weight, power requirements that you have. Nominally, you said, we were given the weight. We think we can do 12 pounds without any problem.
A standard ratio of payload to vehicle weight that you guys use as a guide, as a planning principle?
I would say that for a 12-pound weight, we are looking at about a 30-pound vehicle.
That's good.
For the where it has to fly and how long it has to fly.
Clay, let me open up for you.
Yeah, how do you communicate with the test vehicle, and then what are your expected flight durations of that?
We communicated using a 900 megahertz radio with and we had a tracking antenna on the ground. And what was the other question? I'm sorry.
So everything's line of sight with the communication?
Yeah, but 900 megahertz, we were out at probably 60 to 80 miles away.
Okay, and what is the expected flight duration for your flight vehicle?
If you use the two balloon method, just under the balloon, I think we might be able to loiter, get about 4 hours of loitering from the balloon, and another 2 to 3 hours of loitering with the battery.
Great, thank you so much. That ends our question period. And I just want to say thanks to CalSCott Engineering for presenting. We are going to have an 8-minute break, and we will see you back with Kyberdyne here in 8 minutes. Thank you.
Appreciate it, Andrew. We'll be at the top of the at 2:10 Central, I guess. Depends upon where you are.
Yes, yes.
At 3:10 Eastern. Okay. Claire, you back up?
Yeah, I'm here.
Awesome. Gavin and Ben, are you up?
We're good here.
Awesome. Angela, I think we're ready to rock and roll.
Great, we'll get the pitch loaded up here and then we'll let it go.
The Silicon Valley Aerospace and Defense startup focused on building stratospheric balloon platforms in support of our StarNet. The stratospheric balloon-based communications systems are mesh network designed to augment the DoD space layer. Today, I'm introducing our flyback vehicle, which was designed in response to the Project STAPEL challenge. The flyback fulfills all Project STAPEL requirements through an innovative approach focused on simplicity in order to deliver a tactical balloon system that is easy to produce anywhere, supremely cost-effective, rapidly deployable, and can be launched from austere environments. Our balloons were designed with soft users in mind. They must be simple to unroll, fill, and launch with only one person, and ruggedized and resistant to both failure and user error.
The biggest challenge with balloon development is core design. As balloons scale in size, the core process becomes exponentially more difficult, requiring larger assembly areas and significantly more touch labor from a skilled workforce, compounded by very low production rates that limit automation investment. The cores themselves can be difficult to handle and align and generally require delicate handling to prevent unbonded seams, pinholes, or other damage to the system. Therefore, we opted to focus on a simple method that reduced manufacturing complexity and was capable of forward-deployed assembly and launch. Our system takes a flatter form akin to a bag of chips, with the double LDPE wall to obviate the need for detailed receiving inspection and repair. The balloon is joined with tin-and-filled rolled seams that are heat shrunk and taped to maintain a seal. This results in a thick, rugged seam that can tolerate rough handling and aggressive launch conditions. The balloon itself boasts a 8x lift-to-weight ratio at the current scale compared to more complex core construction balloons. Our system is capable of being launched by a single operator thanks to our innovative sandwich-weighted launch pulleys with hands-free initial lifting gas bubble placement and protects the balloon from wind damage until launch. This system requires minimal footprint and can be deployed from the back of a flatbed truck or roughly any 14 by 20 foot clearing. The balloon is packaged to facilitate rapid setup with low probability of damage requiring no advanced training. Once deployed, the launch system can be repacked in a matter of minutes, thus minimizing impact on element movements. The flyback matter exceeded all of the 9 required features called for in the Project STAPEL challenge. Of the 9 remaining desired features, we met 6 of those requirements. Addressing 2 of the ones we didn't meet will include a semi-customized COTS power bank in the demo flight with a 100 watt-hour capacity and no-spec bayonet lock fittings. The total cost of our system as built was less than the desired $1,000 per system, with the bulk of that cost being the helium lift gas. If you switch lift gas to hydrogen, the total cost drops to roughly a quarter of the previous cost. All our materials were COTS, and in full reproduction, we can drive down costs by securing raw materials discounted direct from the manufacturer and improve touch labor efficiency. Here are some of the more images of the innovative weighted sandwich system taken during the flight test launch, consisting of a dual tarpaulin lower ground cover and upper tank used to hold down and protect the flyback during the build process. The flight test used to demonstrate TRL-7 capability was executed on October 18th, shortly before 1:30 p.m. local time, launching from below the San Luis Reservoir Dam and flying for almost 3 hours before landing just north of Santa Cruz, California, roughly 120 feet up a Douglas fir tree. Minimal systems were included on this flight test, and the balloon was filled to a significant portion of its total volume to ensure balloon seam failure at a lower altitude and recoverability based on the day's conditions. This led to a significant excess lift condition and rapid rate of ascent, which the system managed gracefully.
Our company was formed around the belief that we will lose satellite coverage in the next conflict. We believe stratospheric systems are best positioned to provide over-the-horizon communications and sensor coverage that approximate satellite performance and provide several advantages over satellite systems. My name is Austin Holbert, and I'm the CEO of Kyberdyne. I served as a fighter pilot prior to leading active duty for Harvard. Previously at Hybridyne, I worked at McKinsey & Company, doing work in aerospace and defense strategy, manufacturing, and supply chain operations.
And I'm Ben Clam, the Chief Technical Officer. Prior to joining Hybridyne, I worked at LTA Research and Exploration, where I was employee number 2 and helped lead the production of the world's current largest aircraft, Pathfinder 1, which recently took to the skies from Moffett Field, California. Together, we bring more than 25 years of experience in the aviation industry and an unmatched drive to push the boundaries of stratospheric exploration.
The Hybridyne team is perfectly suited to deliver innovative solutions in the high altitude ballooning space. We look forward to answering your questions.
Ben, Austin, appreciate you joining us. Really interesting technology. Let me open up to Clay and actually let me go with Ben and Gavin first. I'll come back to you here, Clay, in a sec.
Yeah, thank you, gentlemen. I think the chip bag design is really interesting. What I think I saw is sort of like a canvas bag that the envelope comes out of after it's filled. Is that correct? So that stays on the ground?
Yeah, basically there's a tarp. It's not a canvas bag, it's a tarp that acts like a tent and basically the ground so that it's basically at ground level until you're ready for launch.
Okay, yeah, that makes sense. As far as your StarNet payloads that go onto the platform itself, what does your C3 architecture look like for the balloon in its current state?
Austin, you want to grab that?
Yeah, we're still kind of taking customer calls. We're working with the CDAO office right now at the Pentagon to kind of develop what they want as part of the kind of next gen JADC2 architecture. So our overall philosophy is to keep it open source and unclassified, so that way it's shareable. So we can integrate partner nations without having to worry about getting people into classified networks. So it will be an open source. It will most likely be software defined radio, kind of similar to Link 16, but just unclassified.
You guys advertised a ratio of 8:1 for the envelope to the payload. What do you see as kind of the upper limit for this current geometry?
That's a great question. We haven't done a deep analysis to understand at what level the seam would actually fail, at what kind of like super pressure condition it would fail, and exactly how big you could make these systems.
What do you feel is safe?
And so essentially probably at least a 1.5x, so probably a 50% expansion of the total volume of the system would be more than easily handled by the current seam process. A 2x is, say that again?
Can you give me a mass, a weight?
Yeah, and so scaling it up by roughly 50%, you would exceed the 50-pound capability.
Okay.
The current system can do probably about 25 pounds to about 45,000 feet. And so, right, you could do approximately the same with a larger balloon with about 50-pound payload.
Any issues to scale, or what are you looking at scaling?
None at all. So essentially the scaling process would be lengthening the system, right? The manufacturing process would maintain the same geometry. You would just make the balloon longer, essentially taller.
And can you remind me just approximately how many you guys can produce a month?
It takes a team of 2, roughly 2 hours to produce one balloon. And so it is entirely based on your manufacturing team scale size.
And we'd probably optimize that down to get it much quicker.
Clay, let me open up to you.
So getting back to that production, so you guys aren't currently ready to start scaling out 1,000 units a month. You would take some time to build up to that?
Correct.
And then it seems like your system is still in its initial testing. What do you estimate the TRL for this is?
Well, I mean, based on our first flight tests, technically it would be TRL 7, but we would want to do a lot more reliability testing to continue to validate the durability or the flight time envelope, so that we can guarantee that the max duration could be achieved.
Okay, and your bag concept is really interesting to us. Does that bag size and weight account for lift gas?
It does. Yeah. So that excess lift was as measured.
Yeah, I saw a picture in your deal where you compared it to a Cabela size a large bag, like a backpack, so that
Sure.
contains lift gas within it.
So that's just kind of the part of the inspiration for the basic geometry.
Okay.
Yeah,
The lift
and
gas
so
would
the actual package valise would be much larger than that, right? So it wouldn't be something that you would necessarily pack on your back in a way that was to that scale. It would be a much larger roll, but you could carry it by one person.
Copy. And then I liked your launch concept with the securing down of the balloon. What do you estimate your wind cutoffs are for launch?
50 knots is sort of the guaranteed. We haven't had the opportunity to explore the top limit. And so that would be another kind of area of development, would be exploring just how high of a wind we could launch in.
You said 15 or 50, 1.5 or 5.0?
1.5. The day that we launched, surface winds were gusting to roughly 10 knots, and we didn't have an issue. So
Great, thank you so much, Benjamin. We are at time. I just want to say thank you for your presentation today, and we are going to go into a 2-minute break, followed by Near Space Labs. Thank you so
Appreciate
much,
it, guys.
Benjamin.
Thanks, everyone.
We're ready to go, Angela.
Great, thank you. So we're going to hear from Near Space Labs and hear their presentation next.
Ignacy from Near Space Labs. I'm happy to be here today introducing our technology and experience in stratospheric operations. I'll be using slides that have been adapted for public use and might be a bit different from the submitted ones. After the demise of the Google Loom project a couple years ago, Near Space Labs is now the largest stratospheric operator in volume. We do more than 300 operations every year, both in the US and Europe. And our total now is around 600, 700. And usually what we do with these missions is imaging, that is, Earth observation with a unique combination of high resolution and frequency that is really attractive to our users, both in the commercial and civilian government space. A few other facts: we're a venture-backed company with 20 million raised in capital since 2017. And we have a headquarters in New York and a small technical office in Spain, from where I'm talking today. At the core of our operation lies the Swift, our balloon-based flight vehicle. It's a Tirolana platform, as I'm saying, proven in more than 600 flights, and it can stabilize in between 20,000 and 80,000 feet. This vehicle flies on a standard disposable balloon, and in here we're really taking a bit of a unique stance in the industry, because as a business we really have to care about our margins. there's nothing more cost effective than weather balloons for this operation. So we're taking it upon ourselves to transform them into highly maneuverable systems with our altitude control system that bends helium to be able to stabilize at these different altitudes and stay there. We now have a payload package consisting of a visible band camera, but in general, we can fit up to 150 watt-hour battery payloads and fit them for about 8 hours. We usually do, daylight operation, so that's about an 8-hour operation. And we're flying in a 12 pounds configuration, but with minimal development, we could go up to 30 pounds takeoff weight. At the end of the mission, what we do is we jettison the balloon and the vehicle autonomously returns to base, and this really sets our solution apart, right? As opposed to a common balloon operation that results in an uncontrolled landing, our vehicle is steering with pinpoint accuracy to 100 yards to land in a specific place in the ground, and it can even go against prevailing winds. This is really a special thing, a significant advancement in the field, and I would love to talk about this more in a confidential setting. These operations that we do had to be nimble from the start to be able to scale our imaging product. So, by the way, on the right, you have a visual on how the images look like, the product that we are making. And on the left, you have an example of how nimble we had to do. So literally, we can launch from a patch of dirt with a small crew of 2 people. In our normal commercial operations, we fly with transponders and work with FAA. So in the middle, you have an example of 4 of our balloons on radar in the north of Florida, amongst other air traffic. The flight of our balloons is prepared and controlled with our in-house software that can predict, plan, receive telemetry real time, and also send commands to the vehicle as it goes for imaging nodes, for altitude changes, updating landing target, and all of those things. As far as manufacturing, we already, internally for our own usage, we build a few units a month in a really small facility of 100 square feet. But with these limited volumes that we have now, you can already see the bill of material is on the order of 10K. So while manufacturing this vehicle is inexpensive and it will get even better at volume, it is important to mention that the recoverability and reusability, even across hostile areas, changes this cost-benefit equation. So long story short, what we're saying here is the price point would be okay for an attritable platform, but it doesn't even have to be an attritable platform in our case. Last but not least, here you have the leadership team that makes this possible. We bring experience both from large aerospace companies and also modern product-oriented companies like Google. So our unique blend of proven commercial technology, a reusable package of 12 pounds, fits already most of the requirements of STAPEL, and with minimal changes is absolutely ready to transition to ISR and other defense missions as needed. Thank you very much.
Appreciate it. Let me open up to Gavin and Ben.
Thank you. I really think the latex pairing up with an airfoil is really interesting, so that it's not consumed in use and you can recover that with what sounds like 100-meter accuracy. I'd like to understand how long a typical flight lasts after it's deployed from the latex balloon. What's the endurance of the system as it glides?
Yeah, that's a great question. So there's 3 phases in flight, like the ascent that goes like any normal weather balloon. And then with this altitude control system I was mentioning, we stabilize at a pressure altitude. And we need to do that because we make imaging and we need the resolution of the images to be consistent. So we have to take them from a specific altitude. And once that's done, once we have flown over the area of interest, and again, this phase of imaging can be a few hours. We do usually 4. It could go up to 7. Then we jettison the balloon and we do this descent on this steerable paraglider. And typically from altitude, from 60,000 feet to ground, it's going to take an hour and a half, something like that, to get to the ground, right? And usually we reach the target and we just like on the last phase, we just spiral and wait for the, for the system to go down. So it's a glide ratio of like around 3.
Okay, thank you. That was really helpful.
Thanks, Gavin.
Any issues for scalability? I mean, you're able to produce, right, approximately 100 a month. What's what would you need in order to be able to scale to get to or how long would it take you to scale to, let's say, 1,000 a month?
Yeah, that's a great question. So I think, we can be really realistic with, we have a small manufacturing floor and we are very aware of real life supply chain problems and what does it take to really make 1,000 of anything a month. And I'm talking about the vehicle, right? So it has all of this navigation, GPS, SATCOM, it has all these things, right? So I think what I have here and what we have from last time from the form, I think it probably is going to take 18 months or something like that to be at 1,000 level churn, right? But as far because of this project, we look at our supply chain and it is capable of supporting that. So it's more of facilities that we would have to expand to get there.
Appreciate it. Clay?
You guys don't make your balloons in-house. Where are you getting them from?
So we have a US supplier and we have like a deal for like 400 a year, something like that. Yeah.
So if you do scale to 1,000 a month, you would need multiple suppliers.
I think they're fine because those guys, I mean, they're pretty well known. It's Cayman Balloons, and I think you can Google them, and they support all of the weather operations for NOAA also. So I'm sure these guys churn out 1,000 a month. So we're not even the largest customer. So I think we would be okay.
Okay, thank you.
Ben?
I think you already covered it, but can you reiterate what's the payload capacity underneath the system?
Yeah, great. So what I'm talking, I have two points there. There was the takeoff weight of the system, and the different thing is the payload. So at takeoff, so everything that is hanging from the balloon, right now we use 12 pounds configuration, and we have gone up to 30 pounds hanging from the balloon. If you look at payload, so if you want to retain all of our navigation, the steering to the return to base, the GPS tracking, the SATCOM, then you're looking at payload inside the vehicle, which is right now our camera system. And that is approximately 50% of the device. So when I say 12 pounds takeoff, it's 6 pounds payload, and then 30 pounds takeoff weight, approximately 15 pounds of payload we would accommodate. Hope that makes sense.
No, that was perfect. Thank you very much.
Yeah, thanks, Gavin.
I wonder, just out of left field, is there an opportunity for on that payload, that platform, to put maybe like a small motor on it so that it could maybe go against the wind to glide, right? You want to take a picture of an area, but you don't want, let's say, satellite of the water, right? And you're approaching from the land to the water. You don't want to land in the water. You actually then want to eventually turn around and go against, right? But you have to go against prevailing winds, right? Thought about, because you have this novel platform, to be able to actually put a motor to be able to do something like that.
I think that's a great question, because we developed it because we had to do coastal imaging operations. Like, customers want New York, they want Miami, they want, Los Angeles. So it's by the sea. So you need to be able to return against prevailing winds sometimes. And actually, the paraglider itself, and it depends on, of course, all sorts of atmospheric conditions, but can return against prevailing winds. And I think that is really something that even ourselves had a hard time wrapping our heads around, that if the wind is not super strong, it can recover against headwind. But as you say, if you get an engine twin, a propeller, like a motorized paraglider, it could get a lot more range. And this is something that it's not difficult. We don't do it nowadays because as far as FAA classifications, etc., we work in the civilian airspace, and it would be, they don't even know a stratospheric motorized paraglider. It would be its own thing regulatory wise. So that's why we're not going there. But I think in different operational theaters, that's something that could be absolutely give more range to the system. Yeah.
Appreciate it.
Thank you, Ignacy. We're at time. Thank you so much for coming and for your presentation. We're going to go into a 2-minute break.
Perfect. Thank you.
Hey, Angela, we're ready to go.
Great, thank you. We're going to hear from Zenith Aerospace next and get their pitch pulled up.
My name is Eric Campbell with Zenith Aerospace. My background is with the U.S. Army, where I saw firsthand the challenges associated with the resourcing of operational and strategic ISR and the limitations related to ISR endurance in terms of providing persistent surveillance. That is why I'm enthused to be a part of the Pegasus ultra-long endurance, high-altitude unmanned aircraft system developed by Zenith Aerospace. Zenith Aerospace was started by a small group of aeronautical professionals after meeting at the Stanford University Structures and Composites Lab. Their focus has been the development of the Pegasus stratospheric UAS so that it is a dual-use technology able to be employed in both the commercial and military sector. Since meeting 10 years ago, they have spent considerable time raising capital, iterating the aircraft development, building DoD past performance, and developing their team with further expertise. Pegasus is a lightweight hybrid electric diesel UAS. The aircraft has a 100-foot wingspan and is specifically designed to operate in the stratosphere in 99% of all weather and wind conditions, which makes it an ideal platform for use in various geographic combatant command areas of responsibility. Pegasus is designed to carry modular payloads with 3 payload bays available to mount sensors of interest. The total payload weight capacity is 165 pounds, and the system provides 250 watts continuous power to the sensors. The Pegasus will have 5 days of endurance at 60,000 feet and 8 days of endurance at 20,000 feet. Zenith Aerospace is also designing the aircraft to support the solar cells on the wings, which would result in increased endurance. The technology readiness level of the aircraft is 5, and we are currently building the lightweight composite structures of the aircraft. Additionally, in our facility, we have built a full-scale Iron Bird mock-up to model how system components will be integrated. The team has flown a smaller scale prototype of the Pegasus and has conducted several tests of the high bandwidth, low latency communications payload used to communicate between multiple Pegasus aircraft and transfer data between the air and to the ground. Potential funding and endorsement from NSIN and the U.S. Army Space and Missile Defense Command will support development of the powertrain and complement our existing partnership with the U.S. Central Command and Air Force Special Operations Command. Our team is planning a demonstration of the Pegasus in April 2025. Pegasus is an excellent candidate for the U.S. Army Space and Missile Defense Command as a strategic ISR platform which supports joint all-domain command and control. With its stratospheric operational altitude, Pegasus can conduct deep sensing to monitor or target over greater distances than legacy ISR systems. Logistically, its modular payload capacity and 3 payload bays allows for multi-mission capability. The Pegasus has a small footprint in terms of size and requirements to operate. It can take off and land on short runways and is able to be transported in a 40-foot shipping container for expeditionary operations. Zenith Aerospace is building past performance and momentum with the DoD related to our Direct Phase 2 Small Business Innovative Research Award for development of the Pegasus high-altitude stratospheric UAS. This effort is endorsed by U.S. Central Command and managed by Air Force Special Operations Command. The effort will result in the demonstration of the Pegasus at the culmination of the 18-month timeline. In closing, Zenith Aerospace appreciates the opportunity to pitch our technology to NSIN and the U.S. Army Space and Missile Defense Command. We hope that you see the military relevance of the Pegasus aircraft to further the high-altitude capabilities of the U.S. Army, Joint Force, allies, and partners. Thank you.
Awesome, appreciate it. Gavin?
All right, thanks, gentlemen. So I only have one question, and it's if you can make this smaller. So I saw the 1/3 scaled option, but as far as this competition is focused on smaller systems. So
yes.
I wanted to see what your thoughts are on on what's that smallest capability.
Yes, I understand. So we're kind of more like out of the box solutions. So right now the aircraft has about 100 feet wingspans. I think we can develop something between 30 to 100. The challenge is more, the smaller you are, the less efficient you are, and basically reaching the altitude, have the meaningful payload becomes more challenging. I think what we offer is more, we did not cover it in the deck, but we offer is more kind of, we can provide the service directly. So instead of, you have to buy the hardwares, you just tell us where to fly, we can carry the payload and do the missions. So that's kind of, if you look at the cost per missions, we are comparable to those balloon solutions. But again, like we have, as we show in the deck, we have full manufacturing capability in-house. We have the full teams to develop the aircraft. If there's any specific interest there, a lot of things we have learned developing the Pegasus platforms can be used to develop another platform.
Okay, thank you.
No problem.
Clay?
Yeah, you mentioned that you have a 5-day endurance time. Once you land the aircraft and recover it, what's your turnaround time on that? When can I get it back in the air?
Yes, so so we do have a commercial application that's involving having aircraft fly 24/7 for the whole years. So typical process, when the aircraft land, you probably have 4 hours windows to do everything, including refueling, inspections, and then go back to the missions. I think the shortest time we can do is probably in 30 minutes or something like that. The aircraft was designed more like a Cessna or general aviation, so it's designed to have a very fast turnaround, go back to mission as fast as possible.
Copy that. Thank you. And then what is your launch and recovery infrastructure looking like? Do you need like an established runway? Do you need a vehicle to launch this system? I've seen some of them where they have an infrastructure on a vehicle and from there.
The aircraft have a landing gears, so we definitely prefer to land on hardened surface. Basically, a rule of thumb is most airport where you can fly Cessna, we can land and take off from those space. The aircraft was relatively low speed, so we're talking about like a few hundred yards in terms of length of the runways. So it's very, there's a lot of space in the world that can support our operation.
Okay, thank you.
Also, just to add one more thing, the aircraft have very long range, as you can imagine. It's basically designed to take off, fly to Japan and come back without refueling. So basically we have a lot of freedom to where to deploy the aircraft and where to support the mission.
2 questions. You said it was a TRL-5. How much longer before it actually becomes operational? How much further to get to like a TRL, 7, 8?
So right now we have a very aggressive testing schedules. So we plan to do the maiden flight either late next year or early in 2025. For TRL-5, because all our avionics, most of our powertrain, we're using off-the-shelf TRL-9 solutions. Most engineering efforts is on the aircraft, on aerodynamics designs, which are the fluid in the digital world, and everything is relatively well known to the community. So there's not much technical risk. So that's why we think we're at TRL-5, and we think we can hit TRL-6 or TRL-7 within 18 months.
Awesome, appreciate it. Ben?
We're good here. Thank you.
Awesome.
All right, thank you.
Thanks, guys.
Thank you. We'll go into a 2-minute break and return back with Urban Sky.
Angela, we're good to go.
Great, thank you. Next, we have Urban Sky with Andrew Antonio, and we'll get started with that pitch right now.
One moment, please. So the recording was working earlier when Andrew sent it over, but for some reason it's not loading now. Andrew, is there any chance that you can just screen share that from your end? I do apologize.
Hey, no problem at all. Should I just give the presentation or do you want me to share the video?
If you could share the video, that would be great.
Okay, give me 1 second here.
No worries. I watched it over earlier and it was great, but for some reason now it doesn't want to play.
Hopefully let me try it. Hopefully the audio will work. So tell me if it doesn't. So I'll share it right now.
Yeah, if you leave yourself unmuted, it should.
Perfect. Can you see my screen?
Yes.
All right. And if you could just type in the chat that the audio is okay once I hit play.
Okay.
Hi, everyone. My name is Andrew Antonio. I'm the co-founder and CEO of Urban Sky. My company, Urban Sky, is a leading U.S. developer of completely novel, tactical, and controllable stratospheric balloon systems. The core innovation we brought to market is a small, ultra lightweight, rapidly deployable, low cost, and targeted stratospheric balloon. We call them microballoons, and our DoD partners tend to think of them as their own personally deployable satellites. I'll back up. Before Urban Sky invented the microballoon, there were basically two categories of stratospheric balloons. Those that you see on the left, large, extremely expensive, operationally limited, long duration persistent balloons, or those that you see on the right, small, tactical, short duration weather balloons that can fly really no longer than just a few days and lack effective control or targeted persistence. At Urban Sky, we combined the two, leading to the first ever tactical, controllable, and highly capable stratospheric balloons. These microballoons represent a new category of C4ISR vehicles that can be launched by just one operator from virtually anywhere in less than 5 minutes. They're already carrying payloads up to 30 pounds. The current microballoon is fully operational, is launched over 100 times to the stratosphere, typically for missions of up to about 10 hours in duration. They are stealth with little to no radar profile, operating at altitude ranges between roughly 50 and 70,000 feet. They're extremely low cost, priced at under $15,000 a system, while also being the first ever reusable stratospheric balloons. Several DoD end users are already buying and using our microballoons for flight testing and training today. The microballoon already satisfies almost every single stated STAPEL requirement. Our current system is fully operational, capable of carrying modular payloads weighing up to 30 pounds on shorter duration missions. Within just a few months, we'll be flight testing multi-week missions with smart balloon navigation and persistent maintenance of target areas, and achieving the production rates that are required by this program. The prize money from this challenge would allow us to invest in the only outstanding requirement not met, providing power to modular DoD payloads. We are rapidly improving the microballoon with support from the U.S. Air Force, DIU, the U.S. Army, NASA, and others. Most importantly, we've been funded to introduce long duration persistence and navigation into the microballoon, targeting weeks of flight duration with just one microballoon, plus an altitude control system that will allow for navigating balloons or keeping station above target areas. That work is already underway with initial long duration flight testing stated for this winter. We've also been funded to implement autonomous control, smart navigation, and balloon swarming into the system, allowing one DoD operator to manage a constellation of hundreds of smart microballoons above a targeted area. All of this work is scheduled for completion by late 2024. You might wonder how they're controlled. Well, Urban Skies invests millions of IRAD into developing the most advanced stratospheric modeling software available. Our software allows DoD operators to plan missions based on target flyover areas, and you can see here how accurate our prediction engine actually can be. This graphic shows predicted flight paths overlaid with actual flight trajectories. And this shows the power of mobile deployment with tactical balloons. You can adjust your launch point easily, allowing for precise targeting on more days than ever before. Urban Skies flight and mission control software is already being distributed to U.S. Army personnel in a beta environment. Importantly, microballoons can be pre-programmed to stay within certain operating areas with an onboard redundant termination system that will autonomously initiate termination if you lose comms with the system and it begins to fly towards an area you don't want. These microballoons have massive potential in stratospheric swarming scenarios. Imagine launching 1,000 stratospheric station-keeping balloons at a total cost of less than $13 million. You could deploy that balloon constellation with EO payloads, comms payloads, SIGINT payloads, or even just decoy payloads. Today, the cheapest way for an adversary to bring down a balloon from our altitude range is with the use of a $400,000 munition. That means it would cost the adversary roughly $400 million to eliminate your $13 million microballoon constellation. That's the power of tactical microballoon swarms, and it's a future we're excited to help create. Thank you.
Andrew, thanks for the presentation. Let me open up to Ben and Gavin.
Thanks. Thank you, Andrew. The only question I had with your software is the ability to have that as a standalone system. Any roadmap there as opposed to a server-based system?
Jared, can I hand that one to you?
Yeah. So we've already started to put together potential architectures for that. It right now is a server-based system, but we think with some with a relatively small amount of work, well, we could see a future where we have a standalone system that is able to work in an offline setting as long as wind data has some ability to be ingested into it.
Okay, thanks guys. That's all I had.
Clay?
Yeah, you mentioned that your altitude control feature is coming online now. I've been following your SIBR. When do you guys expect that to be ready for game time?
We've already started doing flight tests on our in-flight valve and started doing ground tests on our baluster. We're expecting by early next year to be doing our first demonstrations of altitude control maneuvers. So around January, February of next year is when we expect the hardware to exist. And then sometime in next year is when we start to be able plan to be able to actually put the system into functional use. But first flight tests have already started.
And how much of a cost difference for each system once that altitude control is in place?
Yeah, we don't expect it to be significant, Clay. In fact, our goal is to try to maintain the current price for the system with added functionality. That'll really come down to the BOM cost of the system. So you may see a slight increase, 10 or 15% on the cost per system, but it will be based on the BOM cost of the new system.
Awesome, thank you. And then did I miss how many you can produce a month? And then is your production ready to do that now, or do you need to scale up in order to hit those numbers?
Yeah, we're partway through an 18-month project in order to scale up to those higher numbers. Our production rate right now is on the order of at most about a dozen a week if we're at full push, but we're in the middle of a funded project in order to sometime in the middle of next year be able to produce at those kind of numbers, and we are already in a big enough facility to do that.
So next summer you'll be able to produce how many?
The goal, Clay, is by next March, April, to be able to produce 1,000 per month if we had the orders at our facility. But the infrastructure will be there to do that by spring of next year.
Thank you. That's all I have.
those are the questions I had as well. Andrew, Jared, appreciate it. And for those that are on the line, just big picture, right? We're looking at a time horizon of the week of December 12th. Obviously, it depends upon weather to be able to do the testing and the down selects for the actual demonstration. But the down selects for this to be able to go will be notified here within the next couple of days. And I would ask the government folks to stay online to talk about the next step in the process.
Yes, thank you, Stoiki. And one more thing before we go, I just wanted to introduce Abigail Desjardins. She is the Ensign Venture Portfolio Director, and she's going to talk a little bit about Ensign before we kick everybody off and have our final discussion. So Abby, please go ahead.
Thanks, Angela. Yeah, and I'll be relatively brief. For those of you who are unfamiliar with the National Security Innovation Network, we are a program office organizationally aligned within the Defense Innovation Unit. We've been around for about 6 years, entirely focused on helping to expose DoD problem sets, capability gaps, challenge topics to entrepreneurs, to students, and to mid to early stage ventures. We have this belief and a principle that we should be exposing these problem sets to folks pretty early in their career and in their company's trajectory, so that as they continue to make pivots, make adjustments to their solution or to their way of thinking, that they are able to do so rapidly. The department can benefit and leverage those solutions in a faster pace than we are currently able to get them. We have spun up this program called Challenges in the past year. It is leveraging DoD prize authority, which permits the United States government to award monetary and non-monetary prizes to industry and to students. It is meant to be a signal to industry that we recognize the procurement cycle in the department is long, arduous, lengthy, and challenging, but we wanted to have a way to signal to say you're working on something great and fantastic, and we really want you to continue working. So it's our effort to provide that back to y'all to say keep up the good work and keep moving in that direction with the solutions that you are developing. It does also permit and satisfy the FAR requirements for market research. And so the government is able to work with the winners and finalists of our prize competitions on prototype OTs, and that is pending funding and desire to do so. But we do ensure that the processes that we follow do permit that as a possibility. That there's no guarantee, but that is a possibility. So with that, I will let you all go. If you have any questions about today's event, about Ensign, about DIU, please feel free to reach out. We are here to answer any questions that you might have. So thank you.
Thank you.
Thanks, Abby. Thanks, everyone.
Thanks,
Appreciate
everyone.
it. If you have the government folks stay online, I appreciate it. Thanks, everyone.
Thank you.